Today we'll discuss questions asked on uniform convergence. It is one of the important topics for real analysis, and almost every year at least one question is asked on this topic. So let's discuss its questions one by one. So the question 1 says that prove that if un for all n belonging to natural number are continuous in a comma b, and if summation un converges uniformly to the sum sx in a comma close interval a comma b, then we are supposed to show that sx is a continuous function in a comma b. So first of all, let's define the partial sum in order to ease out the terms that are there. So let us define that Snx as summation small n from 1 to capital N, or let's make it as S capital N. So let's define S capital Nx as summation over n1 to capital N unx. We have defined it as partial sum, finite partial sum. Now let's use the given information to conclude something. So the first thing that is given to us is that unx is continuous in a comma b. So if what is given to us, that unx is continuous in a comma b, and it is continuous for all n equals to 1 2 3. That is basically for all n belonging to natural number, and we know that sum of two continuous function is continuous. So from here we can conclude that Snx, which we defined as finite partial sum of unx, is also continuous on a comma b. And why so? Because sum of two continuous function is continuous. Next thing that is given to us is, first let's write its definition. So since we got that our Snx is continuous, so we can write it as for any given epsilon that is greater than 0 and any arbitrary point x0 in a comma b, if there exists a delta greater than 0 such that modular absolute value of Snx minus Snx0 is less than epsilon by 3 whenever modulus of x minus x0 is less than delta. We are able to write this because we have concluded that our Snx is also continuous on a comma b. Now the another information that is given to us is that summation unx converges uniformly to the sum sx in a comma b. So what is given to us is Snx converges to sx uniformly. Here U stands for uniform convergence. Now if I write it, it will be equals to, for any epsilon greater than 0 there exists an integer n such that for all small n greater than or equals to capital N, and for all x in a comma b, if my Snx minus sx should be less than epsilon by 3. Now since it holds for all x in a comma b, so and since we have assumed that x0 also, like x0 is basically an arbitrary point in a comma b from here, so this must hold for Snx as this must hold for x equals to x0 as well. So for that we get, for any epsilon greater than 0 there exists an integer n such that modulus of Snx0 minus sx0 is less than epsilon by 3 for all n greater than equals to capital N. This is what we got. Now we are supposed to show that sx is basically continuous in a comma b. So what exactly we are supposed to show? So our claim is that modulus of Sx minus Sx naught is less than epsilon whenever modulus of x minus x naught is less than delta, and here epsilon is basically any arbitrary positive number. Basically epsilon is any given positive number which is greater than 0. Now if we evaluate this, basically let's calculate this, that is Sx minus Sx naught. So what we can do is we can write it as this as well, like Sx minus Snx plus Snx minus Snx naught plus Snx naught minus Sx naught. So what we just did is we just added and subtracted Snx, and we added and subtracted Snx naught. Now using triangular inequality, this must be less than or equals to Sx minus Snx plus Snx minus Snx naught plus Snx naught minus Sx naught. Now if you see that we have already concluded from the given information that Snx is basically a continuous function because unx is given to us as continuous. So using that, or let's just name that equation, let's name it as 1 and this one as 2 and this one as 3. So if you see that using 1 we got that Snx minus Snx naught is less than epsilon by 3, that is basically this term. Likewise Snx naught minus Sx naught is less than epsilon by 3 using third. This one is basically also less than epsilon, and using 2 we concluded that this one is also less than epsilon by 3. So this whole thing is less than epsilon by 3 plus epsilon by 3 plus epsilon by 3, and this condition holds whenever basically this x minus x naught is less than delta, whenever x minus x naught is less than delta. So from here we got that mod of Sx minus Sx naught is less than epsilon whenever absolute value of x minus x naught is less than delta, and this is what we are supposed to show. So from here we can conclude that Sx is basically a continuous function. So from here we have concluded that Sx is continuous at x equals to x naught, but since we have chosen our x naught as arbitrary from closed interval a comma b, so from there we can conclude that Sx is continuous on the whole interval a comma b. So that's what we were supposed to prove. Let's move on to discuss the next question. Now the next question is, suppose fn is a sequence of functions defined on closed interval a comma b, and another thing that is given to us is limit n approaches infinity fn x is equals to fx, and it holds for all x in closed interval a comma b. And further they have given us that Mn is defined as supremum of fn x minus fx over closed interval a comma b. So the first part of question is, so our claim is fn converges to f uniformly on closed interval a comma b if and only if Mn approaches 0 as n approaches infinity. So it is fn converges to f uniformly on a comma b if and only if Mn approaches 0 as n approaches infinity. This is our first claim. So let's prove it first. So let us prove the forward part first. That is, let us assume that fn converges to f uniformly on closed interval a comma b. So if I write its definition, that is, for any epsilon greater than 0, for given epsilon greater than 0, there must exist integer n such that modulus of fnx minus fx is less than epsilon for all small n greater than capital N, and it holds for all x in closed interval a comma b, because this is uniformly convergent on closed interval a comma b. Now since this difference holds for all x in closed interval a comma b and for all natural number, for all small n that is greater than the integer capital N, so from here I can say that it must hold for supremum of fnx minus fx. Like this relation must hold because it holds for all x in a comma b. Supremum is over closed interval a comma b, and in the question itself they have defined that this term is basically this term is equals to mn. So from here what we got is basically mn is less than epsilon for all n greater than capital N. So from here we can easily conclude that mn approaches 0 as n approaches infinity, because I can write this information as mn minus 0 less than epsilon for all n greater than equals to n, and this is the definition of limit as n approaches infinity. So from here we can easily conclude that mn approaches 0 as n approaches infinity. So this completes our forward part of the proof. Now let us look at the converse part of the proof. So in this case we'll assume that mn approaches 0 as n approaches infinity. So let mn approaches 0 as n approaches infinity, and here we'll show that fn approaches f uniformly on closed interval a comma b. Now if I write its definition, so it will be for any given epsilon greater than 0, there exists an integer n such that absolute value of mn minus 0 is less than epsilon for all small n greater than or equals to capital N. So, and if I write, like, substitute the definition of mn that is given to us in question, that is basically this value. So what I'll get is supremum of fnx minus fx is less than epsilon, and this supremum is over closed interval a comma b, and it holds for all n greater than or equals to capital N. Now since we know that this relation also holds, like fnx minus fx will be less than or equals to supremum of fnx minus fx for all x in closed interval a comma b. So from here, like using these two equations, we can conclude that absolute value of fnx minus fx is less than epsilon for all n greater than or equals to capital N, and for all x belonging to closed interval a comma b. And if you observe that this is basically the definition of uniform convergence of fnx. So from here we can say that our fnx converges to fx uniformly. So this completes the proof of first part of the question. Now let's see what is the second part of the question. So the second part says that if absolute value of fnx is less than mn for all x in closed interval a comma b, and this relation holds for all n in for all natural number n, then we are supposed to show that summation of fn converges uniformly on closed interval a comma b if summation mn converges. So let's see first what is given to us, and then we'll move on to prove it. So the second part is, first thing that is given to us is fnx is less than or equals to mn for all n equals to 1, 2, 3, and this holds for all x in closed interval a comma b. So our claim here is summation n equals to 1 to infinity fn converges uniformly on closed interval a comma b if summation mn converges. So what we are supposed to show, that if the convergence of summation mn is given to us, then we are supposed to show that summation fn from n equals to 1 to infinity converges uniformly on closed interval a comma b. So let us assume that summation mn is convergent. So let summation mn is convergent. Now if we write its definition, so it is for any given epsilon greater than 0, there must exist a positive integer n such that modulus of mn plus 1 plus mn plus 2 and so on up till mn plus p is less than epsilon for all n greater than or equals to capital N, and it holds for all p greater than or equals to 1. So we have written this using the Cauchy convergence criteria, because since it is convergent, so it must satisfy the Cauchy convergence criteria as well. So this is the definition of convergence of summation mn. Now if I evaluate this, that is fn plus 1 x plus fn plus 2x and so on up till fn plus px, so I can use triangular's inequality here. So that will give me fn plus 1x plus absolute value of fn plus 2x and so on up till absolute value of fn plus px. Now this thing must be less than or equals to mn plus 1 plus mn plus 2 and so on up till mn plus p, because they have given to us that absolute value of fnx is less than or equals to mn. For it holds for all n and for all x belonging to closed interval a comma b. And we have just, like, using the convergence definition of summation mn, we have just proved that this is less than epsilon for all n greater than capital N and for all p greater than or equals to capital 1. So from there this must be less than epsilon for all small n greater than or equals to capital N and for all p greater than or equals to 1. So this basically proves the convergence of, so from here we can conclude that summation n equals to 1 to infinity fn x is uniformly convergent on closed interval a comma b. So this proves our second part of the question, that is, if summation mn is convergent, then summation fn from n varying from 1 to infinity is uniformly convergent on closed interval a comma b. So let's move on to discuss the next question. So the next question is to test the uniform convergence of the series. This is basically the given series and we are supposed to check its uniform convergence on closed interval 0, 1. So first let us evaluate its partial sum of n terms. So that will, let's denote it by Snx. So it will be equals to f1x plus f2x plus up till fnx, and here what I have assumed fix is basically equals to x raised 4 divided by 1 plus x raised 4 raised I minus 1. So these are the terms. So if I evaluate the nth partial term, it will be equals to x raised 4 plus x raised 4 divided by 1 plus x raised 4 plus x raised 4 divided by 1 plus x raised 4 raised n minus 1. Now from all these terms I can pull out x raised 4 as common, so I'll be left with 1 plus 1 divided by 1 plus x raised 4 up till 1 divided by 1 plus x raised 4 raised n minus 1. And also if you observe that since all of the x belongs to closed interval 0 comma 1, so from here we can say that x raised 4 also belongs to closed interval 0 comma 1, and 1 plus x raised 4 will belong to closed interval 1 comma 2. So from here we can say that 1 by 1 plus x raised 4 will be something less than or equals to 1. So if you observe that, like, this will basically form a geometric progression with the common difference less than 1. So it will be equals to x raised 4 times 1 minus 1 divided by 1 plus x raised 4 raised n divided by 1 minus 1 divided by 1 plus x raised 4. And if I simplify it, it will be equals to x raised 4 times 1 minus 1 divided by 1 by x raised 4 raised n divided by 1 plus x raised 4 minus 1 divided by 1 plus x raised 4. And this one balances this one, so it simplifies to 1 plus x raised 4 times 1 minus 1 divided by 1 plus x raised 4 raised n. So it will be equals to 1 plus x raised 4 minus 1 divided by 1 plus x raised 4 raised n minus 1. So it will be equals to 1 plus x raised 4 if my x is not equals to 0, but if I take my x as equals to 0, so this will be equals to 0. So from here you can see that, so from here you can see that the sum of partial sum, nth partial sum is basically a discontinuous function at x equals to 0. Snx is discontinuous, or what we can do is we can define it as limit n approaches infinity Snx as this, and let's call it as Sx. So if you see that Sx is basically a discontinuous function at x equals to 0, discontinuous at x equals to 0, which basically lies in closed interval 0 to 1. But if you observe the original series, that is this one, this is a continuous, like a sum of it is a continuous series because every term is continuous in itself, and we know that sum of two continuous function is continuous. So from here we can see that this is not uniformly convergent because this is a continuous series, but the function Sx that we just evaluated by taking calculating the partial sum, which we got as discontinuous at x equals to 0. So from here we can conclude that the given series is not uniformly convergent. The given series is not uniformly convergent on closed interval 0 comma 1. So that's what we are supposed to check. We are basically supposed to test its uniform convergence, and it's not uniformly convergent on closed interval 0 comma 1. Let's move on to discuss the next question. So the next question is, show that the sequence of functions f and x, where f and x is defined as nx times 1 minus x raised n, does not converge uniformly on closed interval 0 comma 1. So let's first check its pointwise convergence. So f and x is given to us as nx times 1 minus x raised n, and it is defined for all x in closed interval 0 comma 1. So if fx is equals to limit n approaches infinity f and x, so it will be equals to, so if you observe that at x equals to 0 and at x equals to 1, f and x is 0. But if I take my x lying in between 0 to 1, so again it will be equals to 0 only, because when x lies in between 0 to 1, so minus x will lie in between minus 1 to 0, and from here we can say that 1 greater than or equals to 1 minus x greater than 0. So from here we can see that 1 minus x lies in between 0 to 1. So, and if we'll take its basically limit, this will approach 0. So it will be basically a 0 times infinity form. So you can just use L'Hopital rule to evaluate this limit, that is nx divided by 1 minus x raised minus n. And you can easily observe that this approaches 0 as n approaches infinity. So from here we can say that our fx is a 0 function only. So from here we cannot conclude directly anything. So let's move on to evaluate this. Basically we'll be using definition of Mn, that is we'll evaluate Mn, that is supremum of this, and we'll check if it approaches 0 as n approaches infinity or not. And if it doesn't approach 0, then we can easily conclude that it is not uniformly convergent on closed interval 0 to 1. So we'll evaluate this. So absolute value of fnx minus fx will be equals to absolute value of nx times 1 minus x raised n minus 0, which will be equals to nx times 1 minus x raised n. And I am writing it without the absolute sign because x lies in between 0 to 1, and for all those values this thing is always greater than or equals to 0. Now let's name it as some y in order to find out the point where it is attaining its maximum value, basically in order to evaluate the point where Mn is taking supremum value. So our y is nx times 1 minus x raised n, and if I evaluate dy by dx, it will be equals to n times 1 minus x raised n plus n square x 1 minus x raised n minus 1 times minus of 1, which will be equals to n times 1 minus x raised n minus n square x 1 minus x raised n minus 1. So it will be equals to n times 1 minus x raised n minus 1. So from here I can take 1 minus x as common. So I basically took n times 1 minus x raised n minus 1 as common. So I'll be left with 1 minus x minus n x. So in order to evaluate its critical point, I need to equate dy by dx equals to 0. So that basically gives me n times 1 minus x raised n minus 1 times 1 minus x minus nx equals to 0. And from here I'll get my x as 1 divided by 1 plus n. Now let's check if at this point the function is attaining a maxima or minima. So to do that we need to evaluate d square y by dx square. So that will be equals to n times n minus 1, 1 minus x raised n minus 2 times minus 1 times 1 minus 1 plus n times x plus n times 1 minus x raised n minus 1 times minus of n plus 1, and this simplifies to minus n times n minus 1, 1 minus x raised n minus 2 times 1 minus x minus nx plus n times 1 minus x raised n minus 1 times minus of, or I can write it as basically minus of n times n plus 1 times 1 minus x raised n minus 1. Now let's take some terms common in order to simplify it. So I am taking n times 1 minus x raised n minus 2 common. So I'll be left with n minus 1 times 1 minus x minus nx minus n plus 1 times it will be plus because we have taken minuses and n as common, 1 minus x, and it simplifies to minus n times 1 minus x raised n minus 2 times n minus nx minus n square x minus 1 plus x plus nx plus n plus 1 minus nx minus x. And if I simplify it, this nx balances this one, likewise this one balances this one, so we'll be left with minus n times 1 minus x raised n minus 2 times n plus n 2n, this x balances this one, minus nx minus n square x. Again we can pull out n from here, so it will be minus n square 1 minus x raised n minus 2 times 2 minus x minus nx. And if I evaluate it at x equals to 1 by n plus 1, so it will be equals to d square y by dx square at x equals to 1 by n plus 1, so it will be equals to minus n square 1 minus 1 divided by n plus 1 raised n minus 2 times 2 minus n plus 1 times 1 divided by 1 plus n, and it will be equals to minus n square 1 n plus 1 minus n, so it will be n divided by n plus 1 raised n minus 2 times 2 minus 1, that will be 1 only. So it simplifies to minus n square times n divided by n plus 1 raised n minus 2, and you can see that this term will be always less than 0 for all values of n. So from here we can claim that y attains a maxima at x equals to 1 divided by n plus 1. And what will be the maximum value? Y at x equals to 1 divided by n plus 1 will be equals to, our y was basically n times x 1 minus x raised n, so it will be equals to n divided by n plus 1, 1 minus 1 by n plus 1 raised n, which will be equals to n divided by n plus 1 and n divided by n plus 1 raised n, which is equals to n divided by n plus 1 raised n plus 1. And if I evaluate basically, so we got our mn as n divided by n plus 1 raised n plus 1. I can write it as 1 divided by 1 plus 1 by n raised n times 1 divided by 1 plus 1 by n. And if I evaluate limit n approaches infinity mn, so it will be equals to 1 by e, which is not equals to 0. So from here we can say that our function f(x) is not uniformly convergent. Is not uniformly convergent because we in the second question or the first question that we proved, we proved a result that f(x) approaches f uniformly if and only if mn, which is basically supremum of here mn is basically supremum of f(x) minus fx. So this fn approaches f uniformly if and only if mn approaches infinity as n approaches infinity. So since our mn is not approaching 0 as n approaches infinity, so from there we can conclude that f(x) is not converging uniformly to function fx. So this completes our question. Let's move on to discuss the next question. So the next question is, discuss the uniform convergence of fnx. So fnx is defined as nx divided by 1 plus n square x square, and it holds for all x belonging to minus infinity to infinity. So first let's evaluate the pointwise limit of fnx, that is limit n approaches infinity fnx. Let's name it as fx. So this will be equals to limit n approaches infinity nx divided by 1 plus n square x square, and if I evaluate it, it will be equals to limit n approaches infinity x by n divided by x square plus 1 by n square, and if I evaluate it, it will approach 0. So I got my fx as 0. Now we'll show that it is not uniformly convergent. So in order to, there are two methods. One is to use basically mn definition again, that is a supremum of absolute value of fnx minus fx. So it will be equals to a supremum of nx divided by 1 plus n square x square. So if we just evaluate it, let's name it as y and evaluate the point, calculate the point where it attains maximum. So dy by dx will be equals to 1 plus n square x square times n minus nx times 2n square x divided by 1 plus n square x square whole square. So it will be equals to n plus n cube x square minus 2n cube x square divided by 1 plus n square x square whole square. So it will be equals to n minus n cube x square divided by 1 plus n square x square whole square. So in order to evaluate its critical point, we need to equate dy by dx with 0, and that basically gives us x square equals to 1 by n square. So from here we'll get our x as plus or minus 1 by n. Now we need to check at which point the function attains maximum and where it attains minimum. So for that we need to evaluate d square y by dx square, that will be equals to 1 plus n square x square whole square minus 2n cube x minus n cube x square times 1 plus n square x square times 2n square x divided by 1 plus n square x square raised 4. Now we can balance out one power from here and here, so it will be 3. So it will be equals to 1 plus n square x square times minus 2n cube x minus 2 to the 4 n square x times n minus n cube x square divided by 1 plus n square x square cube, and it simplifies to minus 2n cube. Or what we can do is we can take 2n square x as common, so minus 2n square x as common, so we'll be left with n plus n cube x square minus 2n plus 2n cube x square divided by 1 plus n square x square cube. So it simplifies to minus 2n square x 3n cube x square minus n divided by 1 plus n square x square cube. Now let's evaluate d square y by dx square at x equals to 1 by n. So it will be equals to minus 2n square times 1 by n, 3n cube times 1 by n square minus n divided by 1 plus n square times 1 by n square cube. So that will be equals to minus 2n times 3n minus n divided by 2 cube, and it will be equals to minus 2n times 2n divided by 2 cube, which will be equals to minus n square by 2, which is less than 0. So from here we can see that at x equals to 1 by n it attains maxima, and similarly you can evaluate d square y by dx square at x equals to minus 1 by n, and you'll get n square by 2, which is greater than 0. So here function will attain minima. So we get maximum at y attains maxima at x equals to 1 by n. Now let's check what will be the value of y here, because that's what we need. So y, which is basically nx divided by 1 plus n square x square. So y at x equals to 1 by n will be equals to 1 divided by 1 plus 1, which is 1 by 2, which doesn't approach 0 as n approaches infinity, because it is equals to mn. So we got that mn does not approaches 0 as n approaches infinity. So from here we can say that fnx, which is equals to nx divided by 1 plus n square x square, is not uniformly convergent, on r, that is minus infinity to infinity. So let's move on to discuss the next question. So the next question is, show that the sequence tan inverse x is uniformly convergent on any interval a comma b where a is greater than 0, but is only pointwise convergent on 0 comma b, that is if we take a as 0. So basically our claim is tan inverse nx is uniformly convergent on closed interval a comma b, and here a is strictly greater than 0, and it holds for all x greater than 0, but only pointwise convergent on 0 comma b. First let's evaluate the pointwise limit, that is fx, which is equals to limit n approaches infinity fn x. So it will be equals to, it will be 0 when x is 0, and it will be pi by 2 when I take my x as not equals to 0. But we'll not consider this because our x is belonging in closed interval a comma b, and here a is strictly greater than 0. So the point 0 is not included in the interval a comma b. So we'll consider fx as pi by 2 on closed interval a comma b. Now let epsilon greater than 0 be given to us. Then if I evaluate absolute value of fnx minus fx, so it will be equals to tan inverse nx minus pi by 2, which will be equals to cot inverse nx, because we have a result which states that tan inverse nx plus cot inverse nx is equals to pi by 2. So this is what we get. Now if this is less than epsilon, then so from here I concluded that cot inverse nx is basically less than epsilon. So from here I got nx is or let's use mn definition. So supremum of absolute value of fnx minus fx will be equals to supremum of absolute value of cot inverse nx. And since basically cot inverse x is a decreasing function, that you can either evaluate directly or you can observe it from its graph. It's like if this is pi by 2, it's somewhat like this, its graph is somewhat like this. So from here also you can analyze that cot inverse x is decreasing function, so its supremum will attain at cot inverse na, because when a is less than b, for decreasing function f of b is less than f of a. So at x equals to a, this will attain basically the absolute value. Now if I evaluate limit n approaches infinity mn, which will be equals to limit n approaches infinity a supremum of absolute value of fnx minus fx, which will be equals to limit n approaches infinity cot inverse na. So it will be equals to 0 only. So from here we can say that our mn approaches 0 as n approaches infinity, and using the result which states that fn approaches f uniformly if and only if mn approaches 0 as n approaches infinity. So using this result we can easily conclude that fnx approaches fx, which is equals to pi by 2 uniformly on closed interval a comma b, where a is strictly greater than 0. This completes our point on uniform convergence of tan inverse nx. But if you observe that if we evaluate like at x, like if we take our a as equals to 0, then you can see that the function fx is discontinuous at x equals to 0. Fx, that is we got fx as 0 when x equals to 0 and pi by 2 when x is not equals to 0. So you can observe that this is basically discontinuous at x equals to 0. So from here we can say that fnx is not uniformly convergent. UC is basically for uniform convergence on closed interval 0 comma b, but it is pointwise convergent there. So that's what we are supposed to show. Let's move on to discuss the new question. So the next question is, let fnx is, so our fnx is defined as x divided by n plus x square, and it is defined on closed interval 0 comma 1. So we are supposed to show that the sequence fn is uniformly convergent on 0 comma 1. So our claim is fn is uniformly convergent on closed interval 0 comma 1. Again we can rely on calculating mn and then evaluating it. So if I calculate the pointwise limit fx, that will be equals to limit n approaches infinity. So it will be equals to limit n approaches infinity fnx, that will be equals to limit n approaches infinity x divided by n plus x square, which will be equals to 0. So if I evaluate mn, which will be equals to supremum of x belonging to closed interval 0 comma 1 absolute value of fnx minus fx. So it will be supremum of x belonging to closed interval 0 comma 1 x divided by n plus x square minus 0, that is supremum of x divided by n plus x square for x in closed interval 0 comma 1. So let's name y as x divided by n plus x square. So if we evaluate dy by dx, so it will be n plus x square times 1 minus x times 2x divided by n plus x square whole square. So it will be n plus x square minus 2x square divided by n plus x square whole square, which will be n minus x square divided by n plus x square whole square. So if I calculate the critical points, that is dy by dx equals to 0, So from here I'll get x as plus minus 1 by square root of n. But since x belong to closed interval 0, 1, I can easily discard the negative value. So I'll take my x as only 1 by square root of n. Now let's check the value of dx square y by dx square at x equals to 1 by square root of n. It will be n plus x square whole square times minus 2x minus n minus x square times 2 times n plus x square times 2x divided by n plus x square raised 4, and I can easily balance out one power by taking n plus x square common from numerator. So I'll be left with minus 2x times n plus x square minus 4x times n minus x square divided by n plus x square cube, which will be equals to, if I pull out minus of 2x, so I'll be left with n plus x square plus 2n minus 2x square divided by n plus x square cube, which will be equals to minus of 2x 3n minus x square divided by n plus x square cube. Now let's evaluate value of d square y by dx square at x equals to 1 by square root of n. So it will be equals to minus 2 by square root of n times 3n minus 1 by n divided by n plus 1 by n. I think x will be equals to square root of n, not 1 by square root of n. So it will be plus minus square root of n, and we can easily discard minus of square root of n. So it will be equals to, so x at square root of n will be equals to minus 2 square root of n times 3n minus n divided by n plus n cube. So that simplifies to minus 2 square root of n times 2n divided by 2n cube, which will be equals to minus 1 by 2n raised 3 by 2, and which is less than 0. So from here we can say that y, which is equals to x divided by n plus x square, attains maximum at x equals to square root of n. And what will be the maximum value? That is mn, which will be equals to square root of n divided by n plus n, which is 1 by 2 square root n. Now you can easily observe that mn approaches 0 as n approaches infinity. So from here we can easily conclude that fnx is uniformly convergent on closed interval a, 0, 1, and that's what we are supposed to show. So let's move on to discuss the next question. So the next question is, examine the uniform convergence of fnx, which is equals to sine x plus 1 times n divided by n, and we are supposed to check its uniform convergence on whole real line. So first let's evaluate pointwise limit, that is fx, which is basically limit n approaches infinity fnx, which will be equals to limit n approaches infinity sine x plus 1 times n divided by n, and I can write it as limit n approaches, or you can easily evaluate it. It will be equals to basically 0, because as n approaches infinity, 1 by n approaches 0, and this term in numerator will always be a finite quantity. Now let's evaluate mnx. So it will be equals to absolute value of fnx minus fx, basically it's supremum over real line, which will be equals to supremum x belonging to r absolute value of sine n times x plus 1 divided by n minus 0, and this term will be always less than or equals to 1 by n, because supremum of sine n times x plus 1 will be always 1, and you can easily observe that mn approaches 0 as n approaches infinity. So from here we can directly say that fnx is uniformly convergent on whole real line, and that's what we were supposed to show. Let's move on to discuss the next question. So the next question is fnx is given to us as 3 divided by x plus n for all x belonging to closed interval 0, t, and we are supposed to state with reasons whether fnx converges uniformly to 0, 2 or not. So we are supposed to evaluate whether it is uniformly convergent in closed interval 0, 2 or not. So for that, first let's check its pointwise limit, that is limit n approaches infinity fnx. So it will be equals to limit n approaches infinity 3 divided by x plus n, which will be equals to 0 only. Now it is clearly you can see that it is pointwise convergent. Now let's evaluate fnx minus fx, or let's just directly evaluate its supremum. So it will be equals to supremum of 3 divided by x plus n, and here x belonging to 0, 2. Now you can easily observe that it is a decreasing function, so supremum will be attained at x equals to 0. So it will be 3 by n, and it approaches 0 as n approaches infinity. So from here we got that mn approaches 0 as n approaches infinity. So we can say that fn sequence is basically uniformly convergent on closed interval 0, 2. And here, since we are supposed to explicitly state the reason for the uniform convergence, so you can state the result which states that mn approaches 0 as n approaches infinity if and only if fn is convergent to f uniformly, and here f is basically limit of fn as n approaches infinity. The next question is this, and it is a repeated question, we have discussed it earlier. Repeated question, so you can just check it for yourself. So the next, let's move on to discuss the next question. So the next question is fnx is given to us as fnx is x divided by 1 plus nx square for all x belonging to real line, and we're supposed to show that fn converges uniformly to a function f, and further we are supposed to tell what is this function f to which fn is converging uniformly, and further we are supposed to show that for x not equals to 0, fn dash x converges to f dash x, but fn dash 0 does not converges to f dash 0. Show that the maximum value of fn dash can take is this. Okay, so first of all we are supposed to show that this is uniformly convergent to some function f. So let's evaluate it by calculating the limit n approaches infinity fnx. So it will be equals to limit n approaches infinity x divided by 1 plus nx square, which will be equals to 0. So this is my function f. Now we are supposed to show that the fn, like given fn converges to f uniformly. So for that we'll restore to calculating mn, because we are supposed to show that we are also supposed to show that the absolute value this can take is 1 by 2 square root n. So we'll use mn, that is supremum of x belonging to r, absolute value of fnx minus fx, and since our fx is 0, it will be equals to supremum of fnx as x belonging to r. Now it will be equals to supremum of x belonging to r, absolute value of x divided by 1 plus nx square. Now let's name it as some y. So let's keep y as x divided by 1 plus nx square. So if I evaluate dy by dx, it will be equals to 1 plus nx square minus x times 2nx divided by 1 plus n x square का whole square. So it will be equals to 1 plus n x square minus 2n x square divided by 1 plus n x square का whole square. So it will be 1 minus n x square divided by 1 plus n x square whole square. Now if I equate dy by dx equals to 0 in order to evaluate its critical point, so I'll get x square as 1 by n. So from here I'll get my x as plus minus 1 by square root of n. Now let's evaluate d square y by dx square in order to check at what point the function y attains its maximum. So it will be equals to 1 plus n x square whole square times minus 2nx minus 1 minus n x square times 2 times 1 plus n x square times 2nx divided by 1 plus n x square raised 4. Now I can easily balance out one power, so it will be equals to 1 plus n x square times minus 2nx minus 4nx times 1 minus nx square divided by 1 plus nx square cube. So it will be equals to, so what I can do is I can pull out minus 2nx as common, so I'll be left with 1 plus nx square plus 2 minus 2nx square divided by 1 plus nx square cube. It will be equals to minus 2nx times 3 minus nx square divided by 1 plus nx square cube. Now if I evaluate d square y by dx square at x equals to 1 by square root of n, it will be equals to minus 2 square root of n, 3 minus 1 2 divided by 1 plus 1 cube, which will be equals to minus square root of n by 2, which is less than 0. So from here we can say that at x equals to 1 by root n, y attains maximum value, and at x equals to minus 1 by square root of n, d square y by dx square will be equals to square root of n by 2, which is greater than 0. So at this point y attains minimum value. So maximum value is attained at this, so mn will be equals to 1 by square root of n divided by 1 plus 1 by n into 1 by n, which will be equals to 1 by 2 square root of n. Now you can easily see that this approaches 0 as n approaches infinity. So from here we can conclude that Fn is basically uniformly convergent. Now the question further asks us to, like, there is another part of question which we are supposed to show that for x not equals to 0, Fn x approaches f dash x, but this doesn't hold for x equals to 0. Now let's see how we can show that. So my Fn x is basically x divided by 1 plus nx square. Now if I evaluate Fn dash x, so it will be equals to, we have evaluated it earlier, Fn dash x, yeah, it will be equals to 1 minus nx square divided by 1 plus nx square whole square, 1 minus nx square divided by 1 plus nx square whole square. Now our claim is to show that for x not equals to 0, Fn dash 0 is equals to, I guess, approaches f dash x, approaches f dash x. So we were supposed to show that for x not equals to 0, fn dash x approaches f dash x, but this doesn't hold for x equals to 0. Now if I evaluate limit n approaches infinity fn dash x, so it will be equals to, it is equals to 0 only. And if I calculate f dash x, which is again I guess equals to 0, because our fx was already 0, so f dash x is also 0. So from here I can say that fn dash x approaches f dash x for x not equals to 0. Now let's check its value at f0. So at x equals to 0, fn dash x will be equals to fn dash 0, which will be equals to 1, which is not equals to f dash 0, which is 0. So from here we can conclude our result. I guess we should stop this video here because otherwise it will get too long. We'll discuss the remaining questions in next video.